Okay, so the last thing that was up on the board was carbon dioxide, and this is an appropriate time for us to stop and take a look at what's going on inside this molecule. Okay. If we look on the periodic table, oh, I should probably draw it a bit bigger. What I'm about to ask is a really, really odd sounding question, and it's something that my 2000 level students get wrong when they start organic chemistry. Organic chemistry is the covalent chemistry of carbon. It's all the stuff that life is based on. And they get it wrong because they just haven't thought a genuine thought.
Is biochemistry and organic chemistry the same thing, right?
Almost. Here's the question. What side of the periodic table is carbon on? Right. Okay. That was easy. And I mean, how many possible answers could there be? 3. Yeah. It's either on the left, on the right, or in the middle. How many groups are there on the periodic table?
4.
8.
8.
And what group is carbon in? 4. And isn't 4 halfway to 8? So what side of the periodic table is carbon on now? It's in the middle. It's in the middle. That was easy. We just had a paradigm shift. Everybody thought it was on the right, and now everybody thinks it's in the middle.
Is this recent or is this for class?
No, I'm talking about the people inside this room.
Oh.
Okay. Unless, of course, we really haven't considered the question. The question is, what side of the periodic table is carbon on? There are 8 groups. I need a better pen. What's the halfway mark? No. The halfway mark is between 4 and 5. The halfway mark is between 4 and 5. So, what side of the periodic table is carbon on? Carbon's on the left-hand side of the periodic table, people. Mind blown. Okay. What side of the periodic table is oxygen on? Here's oxygen in group 6. There's carbon in group 4. This side of the periodic table does something that that side of the periodic table doesn't do. Any hint of a clue as what that is? Right-hand side of the periodic table is electronegative. What does that mean?
It has a bit of a charge.
We defined it. It's been up on the board. What is electronegativity? Electronegativity is in the chemical bond. This side of the periodic table pulls electrons towards itself. This side of the periodic table doesn't. Okay. So when we look at carbon dioxide, I've got a carbon in the middle from the left-hand side of the periodic table, and I've got oxygens on either side from the right-hand side of the periodic table. And those electrons, so those oxygens, are pulling electrons towards themselves. So a new piece of symbolism here. We're going to draw an arrow, and then we're going to put a bar on it. And that's the symbol for electron withdrawal. That's our symbol for electronegativity. And I get one the other way. If you're doing this comparatively and you're looking at multiple bonds relationship to each other, where you put the little sliding bar, that bar is allowed to slide up and down on the arrow, and the further it is away, the more pull it gets. I don't see anybody doing that anymore, but it is a thing. If you dig hard enough, you will see it. Okay, so electrons are being pulled towards that oxygen. That makes that oxygen be a little bit negative. Delta, that's a lowercase delta. Remember, delta is change, and a lowercase delta is a small change. So the outside oxygens pull electrons towards themselves, makes those oxygens a little bit negative. That means that this bond is polar. Bonds can be non-polar if they are made between atoms that do not have significant differences in electronegativity. There is a significant enough gap between group 4 and group 6 to make that bond polar. The more gap you put between the groups, the more polar that bond gets. A carbon to fluorine bond is more polar than a carbon to oxygen bond. A hydrogen to fluorine bond is more polar than a carbon to fluorine bond. Okay? The further those atoms are apart on the periodic table, the more polar it gets. And this is also a polar bond. But the thing about carbon dioxide is this. These electrons repel each other. And I've got 4 electrons in this bond right here and 4 electrons in those bonds right there, because it's a double bond here and a double bond there. They are going to repel each other as far apart as they can possibly get. When you say that this is as far apart from that, what's the angle between these oxygens going to be? That's 180 degrees. If the electrons are repulsive, then the bond angle is 180 degrees. This molecule is linear. In non-COVID times, we would have students get up and hold hands and see if you can tug of war and move the person in the middle. And the answer is pretty much no, because these two forces are equal. They are equal, but opposite. So this bond is polar, and that bond is polar. But overall, they balance each other out. They cancel each other out. So this molecule is linear. It contains two polar bonds, but has no net dipole. So the molecule is non-polar. And this thing about being polar or non-polar couldn't be more important, because polar molecules dissolve in water and non-polar molecules don't. Non-polar molecules dissolve in other non-polar molecules. Do we know any examples of any non-polar molecules? Oil, is that what you said?
Yes.
Because that's what I figured you were going to say. Oil. So we've got oil and water, and they don't mix. And the world of oil is, well, fat contains long, long chains of just carbons and hydrogens, non-polar. So human biology has two metabolisms, a water-soluble metabolism and a fat-soluble metabolism. And if you ingest a poison, and that poison is water-soluble, that's good news, because you can flush that from your system. If the poison that you've ingested is fat-soluble, there's no easy way to flush that out of your body. You're going to have to wait that one out. It's the same with drug testing. You go and get a job. Anybody that graduates and goes and gets a job with any kind of responsibility, they are likely to drug test you at the second interview. And the drug testing will be, oh, we'll take a snippet of hair. Okay. If your drug of choice is water soluble, you can pass their drug test. But if your drug of choice is not water soluble, then you will fail their drug test. Water soluble drugs being like cocaine. Cocaine's water soluble. Marijuana, cannabis is not water soluble. So it's much, much more difficult to trick the cannabis drug test than it is to trick the cocaine drug test. If you fail the test, you'll never drive the bus. So that molecule is non-polar, even though it contains two polar bonds. Okay, this means that we cannot just look at what these molecules give us on paper. We have to consider the geometry. And geometry is a three-dimensional thing. Okay. So today we're going to look at geometry, 3 dimensions. I've got a couple of things that we can do, and then we're going to look at the computer. Who's already run through everybody should have done it by now, right? The lab, the virtual lab where you go and you piece things together. Okay. Because there's a couple of really important things to come out of that, and I will jump back into that. Okay. So here's geometry. Molecular geometry is governed by this set of rules. It's called the valence shell electron pair repulsion theory. And basically what it says is that molecules are three-dimensional, that electrons repel each other. But not equally. That the repulsion between a lone pair of electrons, that's the non-bonding pair of electrons that we see on nitrogens, oxygens, and chlorines, and another lone pair of electrons is bigger than the repulsion between a lone pair and a bonding pair, which in turn is bigger than the repulsion between a bonding pair and another bonding pair. Okay, so those lone pairs of electrons that are not holding the atoms in the molecule together, they actually take up space because they're just pure repulsion. They're not doing anything. They're not involved in a bond. They're not tying two atoms together. It's like they haven't found a purpose yet. So they occupy space and they get in the way. This is something that we have to take into account. All right. Oh, that's nice. The lab manager put new balloons in the drawer. Okay. These balloons are not particularly great, if I remember right. Okay. If you take a balloon and you blow it up, okay, the area inside this balloon represents an electronic orbital. In an electronic orbital, we have a probability of finding the electron somewhere within the boundaries of the orbital. It can never be outside, and it can never be at the nucleus, but it's somewhere inside of here. Okay? So if this is two electrons shared between two atoms, then we don't get to see this atom and we don't get to see that atom, but this is now a chemical bond, right? There are two electrons in this orbital. When the balloons are cheap, the rubber, the latex sticks together and then they pop. So I get like one shot at doing this right. So I'm not blowing them up very big. So if you blow them up big, then there's more surface area for the balloons to stick to each other. Okay, if I stick two balloons together by tying them together, then it does the obvious. They go as far apart from each other as they can possibly go. Just like that. And when I tie in a third one, oh, I'll be able to make this happen. What's that angle? This is flat. Yeah, it's 360 degrees the whole way around. So that's 120, and that's 120, and that's 120. This is flat and triangular. We're going to call that trigonal planar. Here's where the magic happens. When the fourth one goes in, oh, they're already sticking together. When the fourth one goes in, we get our first true three-dimensional structure. So I'm not actually going to tie that, I'm just going to kind of loop it in. That is the same as that, is the same as that, is the same as this. That angle, oh, you've all done the homework. What angle is that? The center, right here, where the knot is not on the desk. It's above the desk. So 90 degrees would be somewhere here. That angle is more than 90 degrees. Don't remember what that angle was.
Pyramid?
It's 109.5 degrees. 109.5, as is that one. These are all 109.5, okay? That's called the tetrahedral angle. This, oh, they're sticking together. This geometric shape is a tetrahedron. It is a triangular-based pyramid, okay? This is a tetrahedron. It's actually cubic. If you put opposite sides, opposite corners of a cube here, then top corners opposite of a cube. That's what you get. The tetrahedral is actually part of cubic geometry, but you don't see that from the outside. Okay. I'm capable of making 4 single bonds. What element am I most likely to be? This element makes 4 single bonds. Carbon. Carbon's a group 4, has 4 valence electrons. 4 unpaired electrons is going to make tetrahedral compounds. All right. If I take one step to the right of carbon, I get to be nitrogen. The nitrogen is in here. These are bonds. There are atoms at the end of these bonds, and then this is nothing. This is just occupying space. This is a lone pair of electrons. It's occupying space. What shape is that?
Pyramid.
Yeah, it's a trigonal, triangular-based pyramid. The nitrogen is in here, and then the other atoms are down there. Okay? So this is what the geometry of nitrogen containing molecules is going to look like. Go ahead.
So if carbon is cubic in nature, but you just,
It's tetrahedral.
okay, so that turns into a pyramid with a tetra. So what's the difference? Because it looks like you just,
I'll draw it up on the board. Maybe it'll make sense when I draw it up on the board. Okay. So they're all based on this so both nitrogen and carbon, still based on tetrahedrons, only one of them doesn't have an atom here because there's no bond here, all right? If I move one additional step to the right, then I get to the oxygen. And oxygen, group 6 valence electrons, but only 2 of them are bonding electrons, the unpaired electrons. The others are 2 sets of lone pairs of electrons. What shape are the molecules based on oxygen? That would be a bond, and that would be a bond. So the oxygen is in here, and then the red part belongs to the oxygen molecule. The white and the blue part are just occupying space. Use your words. What does that look like?
triangle.
This is just L-shaped or bent, right? It's not linear. There's an oxygen in the middle, and then I could maybe have a hydrogen here and a hydrogen there. So if I made water, water is not linear, which is possibly the most important thing to take out of this entire Chemistry 1 class, that water is not linear. If water was linear, then it would be non-polar. But water is not linear, which makes it polar, which means all of those ionic things get to dissolve in water, and any polar molecules dissolve in water. Water is not linear, so it's not non-polar. Okay. Let's put some rules up on the board. If I have a diatomic molecule, that's linear, because I've got an atom here and an atom there. And then the bond is 2 electrons shared between those 2 atoms. So I'm not going to put diatomics on this list. That's just too easy. So I'm going to start at A, B, 2. Like a carbon dioxide. All right. A is the central atom. B is a bond. It's an atom that I bonded onto it. Okay. This gets to be linear. And my angle is 180 degrees. Example would be something like carbon dioxide, or we could put something from group 2, as long as it's covalent. As you move down the group, things become more and more and more ionic. So the only thing in group 2 that even stands a chance of being covalent is the very top of the group, the beryllium. Okay. When I get to have a central atom with 3 bonded atoms around it, my geometry is called trigonal planar. That angle gets to be 120 degrees. These are flat and triangular. There's a molecule called borane. Boron is in group 3. Only has 3 valence electrons, therefore can only make 3 bonds. This is going to break the octet rule. While it's on the board, let's point to that and make an exception out of it. That's an exception to the octet rule. If we take a boron, boron has 3 valence electrons because it's in group 3. And then I put a hydrogen and another hydrogen and another hydrogen around it. That central boron makes all the bonds that it's capable of making, but only has a shared valency of 6 electrons. That's not 8. It's not 8. This has 6 electrons and is therefore electron deficient. When I take a central atom and I put 4 bonds around it, I get the tetrahedron. All of these bond angles are the same. So now what I have to do is come up with a way of drawing this that people can understand. Okay. The red bonds are in the plane of the board or in the plane of the paper, flat. The blue bond is pointing out towards you and the white bond is pointing away from you. So I'm going to use different lines to symbolize in the plane of the paper, pointing out towards you, pointing away from you. Okay? Here's how I'm going to do that. Those 2 are in the plane of the paper. This one with a wedge is pointing out towards you. That's the blue one. This blue bond is pointing out towards you. And then a hatched line. And if you can draw really well, you might even be able to make it a hatched wedge. That is the bond pointing away from you. That's this white bond right here. All of those angles are 109. The actual angle is 109.45. So some books round that down to 4, and some books round it up to 5. Let's just make it easy. All of those angles are 109.5. This is called tetrahedral. What does tetra mean? 4. What does hedron mean? What does this have 4 of? Okay. It has 4 bonds, 4 points, 4 vertices, 4 apexes, but it also has 4 faces. If this is a triangular-based pyramid, it has 4 faces. One at the back, one at the side, one at that side, and then one on the bottom. It's made of 4 triangles. The hedron means face. And then the other thing that we know about tetrahedral geometry is that it is actually derived from cubic geometry. That if I pick a corner and an opposite corner on the top face of a cube, and then the unused corners right there, and I have all of those points meet at the center of the cube, that's a tetrahedron. So when you look at this V, they're flat to each other, they're coplanar, right? And so is that V. And we've told you that all these angles are 109.5, and that's true, but it's a V pointing down and a V pointing up. These two span corners of a cube, and those two span the other corners of the cube. Okay. Anything with carbon. Tetrahedra are the basis of the covalent chemistry of carbon. Incredibly important. Okay, here's what we're going to do. We're going to take one of those bonds away and replace it with a lone pair of electrons. So this is still 4 centers of electron density. 3 of them are to bonds and 1 of them is to a lone pair. So earlier we had a key that said A is the center, B is a bond, L is now a lone pair. There's no bond at the end of it, there's no atom at the end of it, but it is occupying space. And in fact, it's occupying more space than a bond would. So my central atom is still there. I still have these bonds around it, but then I have a lone pair of electrons on the top. Now, a pair of dots on a page with scribbly student scrawl all over it can sometimes go unnoticed. So it's quite common for people to put the lone pairs of electrons in a balloon. That tells us it's there. Pay attention to it. It's not just a pair of electrons. It's not just a piece of scribble on a piece of page. It's actually occupying space. This is now a triangular-based pyramid. This A is above the ground. This is a trigonal pyramid. CH4 is a component in natural gas called methane. Remember, meth means one carbon. Ammonia, NH3, is a weak base. It's in lots of cleaning products. All right. And then we get to A, V2, L2. Which is an A, and it has a lone pair here, and a lone pair there. Can be at any one of those 4 places. And then a B, and a B. This is V-shaped, L-shaped. We've settled on bent. As being a word that everyone can get behind. And our big example here is water. That water is bent. And that's incredibly important. Because oxygen is electronegative. Oxygen is in group 6. Hydrogen is in group 1. Both of those bonds are highly polar and towards the oxygen. Okay, now you can do this with your own fingers. That arrow represents a force. The electrons are being dragged from one end of that bond to the other. And if you've got a force going this way and a force going that way, and they are equal to one another because what's at the end of those bonds is the same. You take 2 forces at an angle and you bring them together. Go ahead and do it. Seriously, go ahead and do it at an angle. The result is your fingers get pushed vertically upwards. All right? What we've got is that diagonal is composed of 2 forces. If you've taken physics, you'll know that you can break any diagonal force into a horizontal vector and a vertical vector. The vertical vectors reinforce. The horizontal vectors cancel each other out. So when these 2 diagonal forces meet, the horizontal components cancel each other out and the vertical components reinforce, and you get a net dipole that runs right up the middle. Individual dipoles, that's the arrow with the bar on it, have 1 line in the arrow. The net dipole has 2 lines in the arrow. And you can put a bar here if you want to. It isn't always necessary. So the green gets to be the net dipole. So water is polar. Okay. All right. In the time we have remaining, which isn't a lot, let's go look at what let's go look at what we have. lab activity for this week. Oh, is that actually hidden? Oh, I'll switch that on. So this is also in our lecture class, as well as in the lab. So you can see it now. If we go to molecular shapes, and if I click here, I should be able to make it go full screen. There you go. We have the option of using little models or going and using real models. Okay, so if I click here, it will tell me what the geometry is. It's linear. And I can, by clicking up here, add. I just added a bond. If I take the bond away, here we go, linear. This is AB2. If I add a bond, I go AB3, which is trigonal planar. If I add another bond, I go tetrahedral. If I take one of those bonds away and make it a lone pair of electrons, then I get the shape for our nitrogens. This is the trigonal pyramid. If I take one of the bonds away and add a second lone pair of electrons, then I get the shape for water, which is bent. Okay. All right, let's take those away and just go beyond what's on the page, on the board. This is as far as we got with what's on the board. But you can go further. In order to go further, you have to bend the octet rule. And we can bend the octet rule with any atom that is larger than phosphorus or larger. The small atoms at the top of the periodic table, they obey the rules. When the atoms get bigger, they can bend it. 5 bonds means you have to have 10 electrons, right? Well, that's a breach of the octet rule, but phosphorus is allowed to split its pair of non-bonding pair of electrons into a bonding pair. So this gets to be a trigonal bipyramid. And then I can add another one. This is octahedral. Octahedral, it's 6 objects, but 8 faces. And the 2 big geometries in chemistry are tetrahedral, it's on the board, and octahedral. All those transition metals that we're going to kind of avoid, they're all octahedral. They all have octahedral coordination compounds, complexes when they're in water. Okay. And we can go through and take bond out and put a non-bonding pair in, take another one out and put another one in. Or we can move on to the real molecules. Here's water. There's carbon dioxide. Here's ammonia. There's methane. Okay. So these 2 little online exercises, they're really, really useful. Okay. They will let you sit and move things around and add. And hopefully it's very clear what the outcome is. Do have a play with them. I know it was an online exercise, and that means, well, there was no deadline for it, so I may not have paid it 100% of attention. Believe me, this is useful. Go ahead, we're done. It's past time. Sorry for keeping you a minute past over.
Do we need to memorize all of this?
I want you to know it. If that means you have to memorize it, then yes. There are 2 big geometries, octahedral and tetrahedral. everything else can be figured out from those two. If you start with those two, you can figure everything else out. Okay?
But do we need to remember the geometry for all of that? Are we going to see things like that in the exam? Where
That. Pronoun, I don't know what that is.
are we going to see
A table. There is a kind.
like this thing right here, and it's going to say,
Oh yeah, you need to be able to. Yeah, that's a two-dimensional representation of a three-dimensional shape. That is bread and butter. That is bread and butter to chemistry. Now that it's been on the board, you are now responsible for that. Wedges, hatch lines, straight lines. They mean three different things.
so what do the wedges mean?
Coming up towards you. And the hatch line means going away from you.
Thank you, bye, Dr. McGuire.